Thank you. Hello, everyone. Do you hear me? Is it too loud? Is it too good? Okay, good. Thank you. So welcome to the talk. It's all about the containers. That's like a pretty fake title, actually, because it would be how to integrate modern containers in a classical system monitoring. But it's all about the containers. It's short and sexy, so it's probably more catchy. So that's why you're here. Quick agenda here. We are going to talk about what are containers. So basically a brief introduction into the container world. We're talking about Lexi, how to monitor Linux containers. And we're, of course, also talking about application containers or Docker containers. Quick introduction about me. My name is Claudio Künzler. Thank you for the introduction before. I live in Switzerland. I report to a master process. For those of you who are married, you know what I mean. And I have 2 kids. I work at NZZ Media Group, that's Neue Zürcher Zeitung. And besides that, I also work at infiniroot.com. I maintain a couple of monitoring plugins. Maybe you know some of them. The one which is probably most known is Check ESXi hardware for hardware monitoring of ESXi servers. So containers. Quick question to all of you, actually. So who has heard about containers? Let's reverse that. Who hasn't heard of containers? Good, so I'm talking to the good audience here. Who has already deployed, doing some testing of containers? Okay, now the really essential question, who is using containers in production? Okay, already 10%, that's good. That's a container. So when we're in the cargo world, we're talking about a unit. A container is a unit size of 1 TEU, which means, or stands for 20 feet equivalent unit, so 20 feet container size. As you can see, there is a double size, 40 feet, exactly the double amount of the container, equals 2 TEU. And as you can imagine, they stack up quite nicely. Stacking them together gives us some benefits on the vessel. There is efficiency. We eliminate use of space between the containers, so more containers on the ship. And we have stability. They don't wobble around as if you would just make one large tower of a container. So stability also equals security for the staff working on board. So they're not like a container falling on the people working on the ship. Comparing to the tech here, when we stack containers, when we are comparing this to our technical world, we will talk about redundancy and scalability. So in a perfect world, the vessel ships out with a couple of thousand of containers, and there's not a storm. There are never high waves. There's never an incident. But, of course, there's a but. The world is not perfect. We have several environmental things we have to consider. We have waves, we have storms, we have technical equipment which can fail, we have human errors which can occur, and containers can fall overboard. So, as a matter of fact, 10 years ago, I was working on at a container shipping company, and there was a brief introduction into shipping containers, etc. And I just had one question after this introduction, and it was, do containers sometimes fall overboard? And the answer was pretty surprising to me. It was just, yes, all the time. Like, just as if it's the most normal thing in the world. And actually, according to statistics, 1,400 containers fall overboard each year. So just imagine 1,400 containers on the ground of the ocean every year. So in our world, our containers don't fall overboard, but they can crash, they can freeze, so we need to monitor them. So what are containers? Again, we need to distinguish first. So there are currently two types of containers. We are talking about Lexi, Linux containers. They are also known as system containers these days. And this is more like a lightweight virtual machine. And we also have the Docker containers, or just containers, as most developers talk to. And these are referred to application containers, and it's mostly a single process started. So if we just look at, in general, containers, a container is a simple process. And of course, every process inside the process is obviously a child process. We know all that. And they use the same kernel. So we have the host system, we have the containers on it, they use the same kernel. We don't have hardware virtualization in between. That makes it really fast. That's why containers are really the way to go these days. We can also set resource allocations and limits using C groups, which has already been a while there in the Linux kernel. And if we think that containers is something new, it's actually not. So we can go way back to FreeBSD in the year 2000. I will skip the first few ones, and I will directly go to Lexi since 2007. Currently, it's maintained by the Ubuntu guys at Canonical. And they, in the recent few years, they adapted a new, an additional name for it. So system containers was primarily used to now distinguish between application containers and system containers, just because there was a little bit of misunderstanding. And Docker came shortly afterwards, actually, and first was based on Lexi until they developed their own lib container and container engine. Couple of years back, since they have been developing their own engine, they have continuously worked on it, and out came actually Containerd. And Containerd is now part of the Cloud Native Compute Foundation of the Linux Foundation, and it's not part of Docker anymore. Let's start with Lexi. So, as I said, Lexi can be compared to a classical virtual machine, like a lightweight virtual machine. We don't have the hardware virtualization, which we gain speed from the direct access to hardware. We usually have a dedicated virtual NIC, which is a bridged virtual NIC into the container. And we usually have the full network access. So what you usually do is you attach your Lexi container, sorry. You attach your Lexi container right into your existing network. So into your existing subnet or wherever you would just plug your machine, like a virtual machine actually. You usually, or you always have your dedicated file system called the rootfs. The best practice is generally to use a logical volume for each container. So you really have your own capacity, you have your own thresholds. In general, this applies to all containers. It's a dedicated namespace for process isolation. So when we're in the container, you cannot see the processes of the host, and you cannot see processes of other containers running on the same host. The big difference between Linux containers and Docker or application containers is the dedicated init system. So you have a real init system starting in Lexi. So as I said, basically a super fast VM, and as it's like a VM, we can just treat it like a typical and classical host. We install our monitoring agents or daemons or SSH or whatever, just as a typical machine you would just set up actually. So monitoring processes inside a container is pretty straightforward. You just launch PS and you see all the processes running inside that container. We also see the init system or the init process of that container with PID1. So as before, like a typical host or VM, just use check procs in that case. File systems is pretty much the same too. Just run df, you see your mounted file systems. You can run checkdisk as before. So now it gets a little bit more tricky. When we're going into monitoring of memory, we have one problem. We have on top, we have the free output or the free command from running on the host and on the container at the same time. We see we have exactly the same value. So how is that possible? The container is using the same amount of the host, which is just not true. And therefore, we cannot really use monitoring or memory monitoring inside the container. Another view is when we are using a command like htop. We see exactly the same amount. So we see the same memory usage. We see the same CPU load. We even have the same uptime of the host and the container. Only the tasks, the number of tasks inside the container differs. Only inside the container you're seeing your own processes. Yet you still see the resources, used resources of the host. Now, let's install LexCFS. Let's try that one here. So with that package installed, we now suddenly see something else or something different. Suddenly, well, the CPU load is still the same, but now we have a different memory usage. We have a different uptime, and as before, the tasks, the number of procs, they still differ. We still have them as before. So what this LexCFS doing is it virtualizes a part of the /proc inside the container. So it gets the real values from the host added inside the container. You have to make sure that LexCFS is actually installed. It depends on your distribution. Already Debian and Ubuntu is a big difference. We see in Ubuntu it's coming as a recommendation. So if you have apt or the settings in apt are to use recommendations, then it will be installed when you install LexC, just the base package. And in Debian, you need to install it manually. Again, the same thing for the free output from before, but now this time with LexCFS installed. So used is not the same anymore, like we saw before in the htop output. So now we can really see what is inside the container and how much memory it's actually consuming. But there is one problem. And you can see on the left-hand side in the column total, we still see the total amount of available memory or total capacity of the host. So now if you calculate the total capacity minus used capacity, you get an available, and that's completely off. So inside the container, as you're not able to see the other processes of the host or the other containers, there's no way a container can know what the other containers or the host itself is using. So just make sure you're not using that value. So when you, or if you want to monitor memory usage inside the container, just make sure of that one column. Just make use the column used memory. Don't use a plugin like checkmem, for example, which makes exactly this calculation. It's completely wrong. An even more tricky way is to monitor CPU usage inside a container. So as we saw before, a container is actually always seeing the host usage. It's exactly the same value. And as of now, it's not possible to have it another way. And there is one which I call a clumsy approach. It's when we compare GIFs. So GIFs is like the time spent on the CPU, for example, in the CPU usage or CPU system in the kernel space. So what we can do is we just get a current value of, for example, time spent inside the kernel CPU, and wait 5 seconds, get another value, subtract the second versus the first, and we get some value. In this case, just 328. So we got 328 jiffys inside or within 5 seconds. If we compare that with the host's jiffys, we can get like an idea how much CPU is this container using of the host's CPU. And just 2 weeks ago, I spoke with Christian Brauner from the Lexi core team, and he said that there will soon be something merged into Lexi code that will allow to correctly monitor CPU usage inside the container. So, fingers crossed. So, to cope with the problems of memory and CPU usage monitoring, I developed Check Lexi. It's actually a workaround plugin, because as long as you cannot monitor that inside the container, you can correctly or almost correctly monitor it at least on the Lexi host. It uses C group values, so it uses a Lexi C group command to check the C group values for each container running on the host. And it also checks the auto start configuration in case you have forgotten it. The memory usage and swap usage is correctly monitored, so you really get the correct value of each container. And as I said, the clumsy approach with the jiffys, it gives you an idea about the container usages of the CPU. So if you deploy Check Lexi in, let's say, Icinga 2, I suggest that you create a variable like bars containers for each Lexi host, and you add the number of containers or the container names on it. And to make it a little bit easier, we can use these values or this array in this case just to apply the Lexi memory check for each container on of that host. In Icinga 2, in the web interface, what we actually gain is a pretty quick overview of all containers, and we almost immediately can see which ones are using most resources of the host. So that's the workaround for that. When we recap Lexi, so it's mostly the same way, but not exactly the same way as a VM. We have to monitor some resources from outside, actually, from the Lexi host. And as I said, soon, whatever that exactly means, but we're talking about weeks, as I was told, that we can use correct CPU resource monitoring. So let's go to application containers. So what an application container is actually supposed to be is just a single process running inside a container. So it's a single application, a single process started up inside a container. It's by default stateless. There is no data or supposed to be data inside a container. You also have a dedicated virtual NIC as Lexi, also VATH. And here is a difference, it's NATed. So we actually run, there's IP tables on the Docker host, which just forwards traffic to the container. We also have a dedicated file system. The difference here is it's by default OFS or OLAFS, and they share the same capacity. So you have like a top-level file system, and all containers are using that top-level file system, even though they have their dedicated root file system. Same as LexiFS or with Lexi, dedicated namespaces. We have the same things we cannot see outside the container. Here, the big difference is that there is no init system, because we are supposed to only run one container, right? And application containers are actually great solution for quickly scaling up applications. So obviously behind a load balancer, otherwise, how you would access them. Another important, or something which crossed my mind lately was we rarely hear Docker anymore these days. We hear Kubernetes, we hear containerd. That's the reason, the reason for that is that Docker actually gave their Docker engine or container engine to the to containerd. So that's the reason why we're currently talking Kubernetes and containerd. Of course, with that solution, we get some additional monitoring challenges, as we are not allowed, or we're not supposed to install additional agents, processes, listeners, etc., into an application container. And additionally to that, we have no direct network access because it's netted through the IP tables. So we could make or configure an expose port for each container to access it via the network. But do you really want to do that if you have thousands of containers? So it means a lot of work, and it's also standalone Docker, just running Docker exec Docker run manually. It means a lot of work. So that's the reason why there's a lot of orchestration tools like Kubernetes, for example, out there, which help you for that. The most important change of mind actually to monitor application containers is that we have to stop thinking as an application container as a host. It's not a host in a classical way, as it has no direct network access. We're talking about a process, we're talking about an application. So we have to think of it as application monitoring and not host monitoring anymore. Ranger is something like a management layer on top of the orchestration. So we have the containers or pods in Kubernetes. We have the container runtime, which creates pods, destroys pods, etc. And we have the orchestration layer, like Kubernetes is one of them, managing the container runtime. And on top of the Kubernetes environment, we have our Ranger environment. So Ranger is like OpenShift, another way of managing your Kubernetes orchestration. What is the reason why is it has a really intuitive user interface and a cool and really good API, so which we use for CI/CD. Before we were actually implementing Docker or application containers, we've investigated more than 1 year of time to really research what kind of Docker solutions are there, how do they cope, how is the licensing fee, is it open source, is it not, etc. So finally we decided for Ranger. And since fall 2017, we're in production with Ranger environments with a total of more than 1,000 containers so far. There's been a big difference also in our production system, which is Ranger 1, version 1. It uses Cattle as an orchestration, as opposed to the new version, version number 2, is completely built on Kubernetes. So there's a big change. And because we're currently only running test and stage environments of Ranger 2, but we're planning to go into production in the next few weeks, we need to monitor our Ranger 2 environments as well. And just if you wonder why I'm talking about Ranger, it's just I'm just a community user. I'm not a salesman or something for Ranger. Quick overview of the Ranger interface. So that's basically a workload or a deployment in the Kubernetes world. You have the overview of your kind of workloads or services. And if we focus on this one here, Nginx test is just a workload with the Nginx image deployed And we're in the next few slides, we will make health checks of that one workload. So the container, or in this case pod in the Kubernetes world, we can monitor it using readiness and liveness probes. So there's two ways of making these probes actually. So the readiness probe means that it tells Kubernetes when the container is ready. So when you're starting up an application, for example, a Java application, which takes much longer time, when am I ready to be included into the load balancing? On the other hand, we have the liveness probe, which is pretty much what we're usually using in monitoring world, is like a typical HTTP get to a status page or something like that. Are you alive? That's all it is. In Kubernetes, we currently have 3 different ways to run a probe or to configure a probe. We can run a simple command, just inside the container, just make, for example, check if a file is available or if it's not there. We can make HTTP checks inside the container, so even when there's no when there's an internal port only, Kubernetes goes into the container, makes these checks for you. And really basic TCP check to just see if the connection can be established to a certain port. When we configure them in the Ranger interface, so we have the readiness check and the liveness check, so we can either set exactly the same, we can set different ones. In this case, it's just a simple HTTP request to /get, so it's just a base path. And we expect a response code of 200 or 300 something. So if we get a 200 or 300 response code for Kubernetes, that means the application is, first of all, ready and it's alive. We also can check the same with kubectl directly. So if we connect with kubectl to our cluster and we go exactly, or we describe the pod, we can see we have here the image nginx, and we have our liveness and readiness checks, which we can see in the kubectl output as well. And of course, we can also check it in the API. So we just use curl to access the HTTP API from Ranger. And we see the readiness probe. Further down below, there would be the liveness probe as well. And most importantly, we have the state, which gives us back the actual state of the container. So if both readiness probe and liveness probe succeed, then we have a running state. So Check Ranger 2 is a new monitoring plugin which uses the API of Ranger. It can, as it's just HTTP or HTTP SXS, it can basically run anywhere. And it currently checks status of the cluster of all projects defined in it, of workloads and of pods, so basically containers in the Kubernetes world. And what I would suggest is that you add in your monitoring system that you add the API endpoint as a host and all the service checks like pods or clusters, for example, or workloads as services under that host object. In the future, or at least I hope so, that we are able to add statistics into the check monitoring plugin or Check Ranger 2 plugin. It really depends on an open issue right now that the API is actually presenting these statistics or resource statistics. So a live example of it was that suddenly we saw that the single pod was suddenly in the state removing. So we saw already that the workload or the service importer was already redeployed, but we still have an old importer pod hanging in the state removing. So, of course, when something like this happens, our monitoring needs to alert me of that. So I'm not explaining all the parameters here, but most importantly, we have the monitoring plugin which alerts me about, oh, your environment is critical, you have a pod importer and the unique ID of this pod, which is in state removing. And because it was still hanging, we had this alert for a couple of hours, and of course we got alerted. It turned actually out to really that it was a pod really frozen, and we need to use kubectl to unfreeze it and to delete it manually. So as a recap of application containers, we're not talking Docker anymore, or mostly not anymore. These days we really have containerd, or we also have runc and kata. That's pretty new, kata, as container engines. And we should not, or we should consider that an application container is not a classical host anymore. It's really just a process, and that's how we have to handle it in monitoring as well. To facilitate your work with application containers, you should use orchestration and management tools, Kubernetes, OpenShift, Ranger, etc., to really help automate your containers and your environments. And the most important point here is to set up health checks, because health checks, that's really the only way to monitor the health of your containers and therefore your container environment. Interestingly, there is also, I saw there are some plugins out there which use kubectl directly, so the command kubectl, which connects directly to the Kubernetes cluster, and it's definitely worth a shot. In our case, we're focusing on the Ranger management, so we're using Check Ranger to pull the API stuff. Some references and links. This is mainly for that when you download the presentation afterwards. And yeah, time for questions. And of course, I'm also still available this evening if you want to have some talk about containers afterwards.
All right, thank you very much. So, any questions? Everyone's still tired from lunch and evening event. All right, when there's no questions, then thank you very much. And as everyone else, thank you very much.
Thank you.
Speaker for the OSMC this year.
Thank you.